From Union.
Okay, good morning, everyone. Welcome to the second day of the Joint Style Symposium. As a reminder, this is an annual event. So we've been holding this event actually separately for CATS and TAL, but starting last year, we're joining them in one symposium over 2 days. As you can tell from the program, today is all about public transit, is all about really the TAL part of the symposium, Transit Analytics Lab. So by way of introduction, my name is Amr Shalabi. I'm a professor in the Department of Civil and Mineral Engineering, specialized in public transit planning and operations. I also serve as the director of the Transit Analytics Lab. So I'm just going to kick off the event today by just some opening remarks, give you an overview of TAL, some of the recent and ongoing work, as well as, just a few things about what's going on in the future. Okay, perfect. Okay, just as a reminder, TAL is actually one of several research centers under UTRI. UTRI is the University of Toronto Transportation Research Institute, under which we have both CATS and TAL, but we also have other research programs and centers, the Data Management Group, which manages the Transportation Tomorrow Survey, the largest household travel survey in the world, 5% of the population. We've been doing this on behalf of many municipalities and organizations within the region since 1986. So we manage the survey. We also manage the data. We have something called the Data Management Group that really is responsible for that. We have the Travel Modeling Group, which is under Professor Eric Miller, that really looks into building all large-scale transportation systems models that are used by the different municipalities as well as the region and the Ministry for Transportation Plans. TAL and CATS, I'm going to talk about TAL. Yesterday was all about CATS, and my colleague, Professor Abdelhai, gave an overview of what it does. We also have CLUE City Logistics for the Urban Economy, which is led by Professor Matthew Roorda, which is all concerned about freight transportation and urban logistics, and also air quality group led by Professor Hatsupolo. So just talking about TAL, TAL has been actually set up in 2020 to serve essentially as a common forum to promote transit decision-making using data and AI-driven analytics. It's really meant to bring together both researchers from various really disciplines, civil engineering, but also computer science, geography, economics, as well as people from the industry, both from the public and private sectors. So that all people who are really interested in advancing data-driven decision-making. So the core idea of TAL is really essentially about harnessing the big transit data that's increasingly becoming available through traditional sources as well as new sources of data. And even this is going to be even more and more in the future with the advent of connected and automated technologies that will also produce large amounts of data. So the idea of TAL is really to harness all this data mixed with advanced analytics from AI, but also simulation and optimization, and also using and leveraging new technologies, like connected and automated technologies, essentially to come up with new and novel solutions to public transit. Imagine really the future of public transit under those new technologies and harnessing the data that we have and trying to address the most pressing challenges to public transit. So just a very quick overview of some of the solutions that we developed using AI. So AI, there's of course different really layers of AI. There's predictive AI, there's generative AI, there's prescriptive AI. So today you'll actually have a taste of some of the solutions that we developed, but very quickly we developed something called ELSA, which is an incident management assistant. That is, you can think of it as sort of ChatGPT for root supervisors. It can actually help them manage incidents as they emerge. And one of the presentations today by Jia Hao will be on that. Transit Talk, which is a large language model framework that really turns requests by riders and staff into conversational answers. Such that we can streamline communication, we can reduce staff workload, and improve and enhance passenger information experience. Transit Pulse is another product of TAL, which again converts and turns noisy posts that really appear on social media like X for people who comment about public transit. So we turn this really noisy posts into structured and station level insights, such that we can really improve, like monitor rider satisfaction, detect emerging issues, and also support data-driven solutions. AI-driven TSP, transit signal priority, that is really based on AI that tries not only to minimize signal delays, but also tries to improve reliability by regulating the headway. We've also done a lot of work with Wi-Fi data and machine learning to construct, for example, OD matrices for across transit networks. iRoam and TAL TAL eBus. Those are two other products that you will learn more about today. So this is just a quick really overview of some of the AI-driven solutions. Sometimes we organize those solutions in one track, if you wish. So for example, to improve surface transit operations, buses that are running on surface streets, which really suffer from a lot of problems in terms of, very slow speed, poor reliability, overcrowding. So we put together some of those solutions such that we can really enhance the performance of surface transit, speed up the operation and make it more reliable, and try to detect, for example, anomalies before they occur, and so on. But more generally, the scope of TAL really spans all modes of transportation: bus, rail, on-demand transit, multi and intermodal transit, at all levels of decision-making, service planning and scheduling, real-time operational management, and ITS and emerging technologies. And the boxes here really talk about the different research studies and products that we developed over the years. You will learn about a few of those today throughout the day. Just a look at the future now. There is a new initiative that is brewing called AI Transit Town. So a lot of the solutions that we developed, unfortunately, do not really see their way through to the industry. So there is a little bit of lack of transfer of knowledge and transfer of technology. So we try to close this gap by creating so-called AI Transit Town. It's a town on the cloud. It's a virtual environment to really advance AI-powered transit solutions. So the idea is to really put all the products that we produce here and even future ones on a cloud, so that if, for example, you are a data scientist with the TTC, you log on and you find that there's a new solution that was really developed, and you can download this because you are a member of AI Transit Town, and you can maybe try it out on some sample data of your own. So the idea is to make our tools available and also create this environment that also enables perhaps mixing some of those tools together. So the pillars really of AITT, AI Transit Town, is really to advance both innovation in AI-driven solutions, enhance training, collaboration, technology transfer, and commercialization. So because this is a town, it has places, so there's going to be a library and school for training, offering, for example, micro courses on AI and machine learning, specifically catered to and customized for transit problems. A playground, which is a space in which data scientists from different transit agencies, along with our own researchers, to be working together on a common problem. A cafe, which is a place for people to chat, and perhaps there will be webinars and so on and so forth. A lab where the innovation really takes place, and also a marketplace, which is a mechanism by which we try to really transfer our products to the industry and so on, which is currently, unfortunately, is lacking. The plan for AI Transit Town is going to occur over 2 phases. Phase 1 is 2 years, in which we set up really the digital infrastructure, the data architecture, also the governance and membership models, as well as seek large-scale funding from federal government and provincial government. Phase 2 is the full launch, which is like in year 3. Again, the idea here is to engage really university researchers and students from all walks of life, not only from engineering, but from computer science, geography, and so on and so forth, economics and management, and also to bring in practitioners, technology specialists and consultants, as well as friends of public transit. So this will be a space for everybody to really meet and collaborate and learn, and maybe also contribute their own innovations. So just stay tuned for this. Before I close off, I just wanted to highlight a very big event that's taking place next year, so-called Transit Data 2026. So Transit Data is really a community of researchers and practitioners from around the world that meet every year to talk about and present their own work on data-driven and AI-driven solutions for public transit. So every year it takes place in a different city. Next year, we're privileged to have it here at the University of Toronto at Victoria College. Both my colleague, Professor Dr. Brandon Hamley, and myself are co-chairing the event. So abstracts, call for abstracts is open. So if you have interesting papers from the industry, especially, we welcome that. So we have it until December 12th. So please consider submitting any interesting work. It's just an abstract, so it's not really a big burden. We're both on social media, and also we have a YouTube channel in which previous events like this one are already online. If you are interested, there's a lot of really knowledge and interesting studies you can follow. So just look us up on YouTube and also on LinkedIn to follow all our events. So with this, then we proceed to the first session. So the first session is all about AI-driven solutions. It's called Propelling Transit into the AI Future. And we're having 3 presentations that are going to showcase 3 products from Transit Analytics Lab. So the first presentation, actually the first 2 presentations is by Jiahao Wang. The first is on iRole with Integrated Route Operation and Anomaly Monitor, and ELSA, which is the Incident Management Assistant that I told you before. So Jiahao is a PhD candidate in the Transit Analytics Lab, working with me. And he holds a Master's of Science and a Bachelor of Engineering in Computer Science. So he's not an engineer, he's a computer scientist. His research focuses on optimizing transit management using advanced methodologies in deep learning and reinforcement learning. He's also exploring innovative solutions and applications of large language models in the field of public transit. Jihan.
Thank you. Good morning, and really happy to be the first to put in the works in here. So the first project we're going to present is the IROM, which is short for Integrated Road Operation and Anomaly Monitoring. And this is the second version of IROM. So the motivation drives us to build this application is that, so we all know that on the roadside, the anomalies such as bunching, overcrowding, and idling are daily struggle for the transit system. And when I come to the transit agency side, when we want to know like why this anomaly is happening, where and when, and how we can solve these anomalies, we need to perform a data analysis and maybe do some predictions. So, but to do that, we have to combine data from different sources, such as APC, AFC, and GTFS data sometimes. And we wish there's a tool that can help us to do such work, to combine the data and to give us some visualization and some insights. So that's where the IROM comes to help. So the objective for the first version, we are mostly focusing on visualization and analysis and enable a integrated investigation for the anomalies. We are not only focusing on one anomalies, but three, including bunching, overcrowding, and idling. And then we are aiming for efficient and easy of use of the pipeline. And for the second version, we are adding another level for the analysis where we're including an anomaly prediction using deep learning method. And the anomaly here is specific for the bunching prediction. So talking about the difficulty of build such project, the build of such application, the first one is come from the data pre-processing. So as we said, the data coming from different sources that using, for example, different keys. So it's really hard for us to align those data together and then to identify like different kinds of anomalies from those data. And then when we finally integrate all the data from different sources, we have to start thinking of what is the threshold, what is the parameters we have to set up for identify those anomalies. And when we finally set up those parameters, we both know that it's not the end. We have to put those into the program we have written, and then we have to derive some like data analysis, and then we have to verify whether this threshold is okay or not, and then we have to come back and tune up those parameters. So this is a lot of work, and IROM could help you with just some simple clicks. So there's some main functions of IROM, like including playback, analysis, and for the second version of IROM, we have a 5-minute bunching prediction. So before we start introducing the detail of IROM's functionality, the data we're using is collected on Road 29, which is one of the highest frequency roads in Toronto, and it serves like 43,000 people per day. I think this data is like 2 years ago, maybe this number is increasing. And it suffers from frequency operational issue. And I believe this route is maybe one of the headache kind of like roads for TTC. So that is the reason why we're picking Road 29 as our case study. So let's first take a look at the playback function of IROM. So here, as you can see, on the very left-hand side is the parameter panel where you can set up, for example, some basic information, which roads you want to monitor, and the direction and the time of the day, and also like the different parameter for the anomalies. And in the middle, we present you the time-space diagram and also the map-based diagram so that you can have a visualization of when and where the anomaly is happening. And maybe sometimes, for example, you can have some idea of why those anomalies happening. So for example, you can see in the very left of this space and time diagram, the blue dots here representing the bunch situation and the green representing overcrowding, and what these red dots is idling. So as you can see here, there's a long time bunching for these two buses. And then the this situation having later resolved at Lawrence Station by holding the falling bus. But because of the bunching, because there's more and more people built up on the road, so there's a overcrowding situation after the Lawrence Station. And also, because it's morning peak, there's more and more people coming to the transit system. So we can see there's overcrowding situation for this two row, and then which leads a long time idling for the hand leading bus, and then these two bus bunch together, and this situation being solved. People online on here. Oh, I'm sorry. Okay. So yeah, as you can see, like this situation has been later solved by also holding the falling bus at the Lawrence Station. So using this playback function of IROM, the transit agency could have like a basic idea of when and where this anomaly is happening and get some idea of like how this anomaly is built up throughout the daily transit service. And then after you set up the parameters on the playback page, you can then turn to use the analysis function. So as you can see, after you set up, and then you can click, I think it's being blocked some on the left. So you can turn to the analysis page where you can select, for example, which stops along the road that you want to focus on. So in here, we are selecting all, but sometimes, for example, here we are choosing the main intersections where we only show the major intersections of along the road 29. And you can select the direction and also what kind of anomalies you want to visual. And here we present to you some basic visualization like spatial and also the temporal based analysis. So you can also have the ability like to pick not only one, but all three anomalies in here so that you can see like how those anomalies interact with each other. And other than that, we are moving one step further, like to give you a more in-depth like analysis in here, like for example, how would the different level of those anomalies affecting the daily operations? For example, the different distance between like to the previous vehicle and different load levels, different speed, and also different schedule offset, like how those those factors like affect the daily service. And then because we have the ability not only like label one kind of anomaly, but three, so that we can actually break down the average bus travel time to different kind of anomalies, and we see like which one they take the most for like to blame. And then the transit agency can think of like which one we can start to like improve. For example, for road 29, most of the time, like for all day service, there's only like 35% of the time the service is running without any problems. And most of the time, the bus is suffering from idling problem, whether it's because like the heavy traffic, there's a lot of people getting on and off the bus at the station, or like being holded by the bus being holded by at the intersection by the signal. So the idling problem could be something that we can target the first. And moving forward, we will talk about the anomaly prediction we included in the IROM. So here we're using a deep learning model called non-stationary transformer, which is proposed in 2022. But even though it's like 3 years or 2 years ago, it's still the best performed model we have tested around like among different kind of deep learning structures. I'm sorry. And then the output from the deep learning model is the bunching risk in the next 5 minutes. And to make the prediction, the input is the vehicle speed, distance to the leading vehicle, and also the deviation from the schedule time for the current bus. But not only that, we're including 3 buses, which is the current bus, its leading bus, and its leading leader. So we're including 3 buses and to have a much more information in the inputs. So this is the prediction results. So as we can see, overall, the accuracy for predicting bunching and non-bunching, the accuracy could be 82%, and the F1 score is 83, which is quite okay. But we want to know where, like, what is the situation that we cannot make a a good prediction? What is the situation that we cannot catch by this machine learning model? So before I really dig deeper into the reason, I want to explain a little bit more about this diagram that you will see later. So here is that we aggregate the input and output data, like in the training data set, into one figure. Like here, the colorful bar in here is showing the inter-vehicle headway. And then this red line, I'm sorry, like it's been blocked by the title in here. So it means the rolling mean delta headway. You can treat it as the headway change. And then this blue dot line means it's the prediction time steps, means on the left of this is the input interval, and then on the left is the prediction horizon. So here, this is we split the whole data set into two parts where there's bunching and non-bunching after the prediction steps. So as we can see from the whole data set, the bunching and for the bunching situation, we can see the headway changing is relatively smooth and there's no sudden change. And also on the non-bunching, the headway between two buses is actually really stable, which is quite similar to the situation that this machine learning model makes the right prediction results. But if we see like this is the situation that the machine learning cannot make the right prediction, is that, for example, in the bunching situation, after the prediction time steps, there's a sudden change between these two buses, between the current bus and its leading bus. And for the non-bunching situation, as we can see, like there's actually the bus is approaching together, and then the distance between these two are not like becomes smaller. So actually the situation for the bunching one is actually the transit agency most interested in, because, for example, if the bus is already really close and they are approaching together, maybe we'll already know that they will meet in sometimes in the future. But for the situation we cannot capture, that could be something be more challenged and be more interesting. So to capture those information and to make a better prediction, we have two improvements of the prediction model. One is that we have reconstruct our training data set to have more edge cases like the one we cannot make a right prediction. And also we're using a random forest at the additional level for including more additional features, for example, the time of the day, the location of the vehicle, and to make the prediction much more solid. And then here is the new prediction results. As we can see, we have a slightly increase of accuracy and also the F1 score. But the most impressive part is that we highly improved the recall of the bunching prediction. And if I'm sorry, I didn't have the numbers in here, but I do a calculation for the precision and also the recall for the non-bunching is a little bit sacrificed, but it's not that much compared to the improvement we got for the bunching situation. So, and for sure, there's like a future works for this kind of dashboard. Like we want to integrate like the prediction model into the dashboard, like to show you like in the future whether there will be a like bunching or non-bunching situation on the road. And also we want to further refine the prediction algorithm to test some new features and to modify and expand the training dataset. And that's it for the iRoom. Thank you.
Thank you very much, Jiahao. So we have plenty of time for questions. For the benefit of those online, if you would like to ask any question, you can use those microphones. Push the button first so that everybody can hear you. And also, maybe if there are questions online.
We don't have any so far.
Open?
Hello, that was great. I thought the dashboard is really inspired the way it goes. Now, how are you verifying the number of people in the bus? Because I know when I use the TTC app, and I'm at 8 weeks now, just public transit. I reset if I call an Uber or use my SUV, but I know that the data they show where they show these the little pictogram is wrong all the time. Did you verify their crowding numbers?
So actually, the number of people on the bus, like the overcrowding, the crowding level, has actually been provided by directly from the TTC, but they give us the crowding level and such. So we didn't actually have the right, have the to verify like how many people are really on the bus. I think it's based on the AFC data they have collected. APC data. I'm sorry. Yeah. That's what they have.
No, they need to fix that data because then this would be really interesting. The second thing is that the drivers really like tailgating each other. Streetcars will actually, the guy will gun it and brake and gun until he's right behind the guy in front of him. How does the TTC tell these people, ease up? And I specifically, I was over at the Daniel School of Architecture a couple of weeks ago, but this happens all the time. And I walked south there and I was going west. And I'm standing there and I'm right there at the time that it says the next streetcar is coming along. And we all know these stories, right? And two had just gone just in front of me. I was actually trying to run to get it, but I don't run as fast as some people. And it was like a game. And I stood there for 45 minutes. And of course, I called customer services, what's going on? Customer service, the TTC can't even see the previous two streetcars that just left. They can tell you, oh, there's a streetcar coming, but they have no idea how many people have to get in and out with accessibility devices. And all it takes is one streetcar. So how does the TTC control tell the streetcar, like that second driver with a 45-minute gap behind him should have been told, ease up. Like there's a huge gap there instead of tailgating right out of there. And he saw people running. I mean, I was trying to run. There was other people, trying to make it because an event had just ended at the Daniel School of Architecture. So how do they communicate? Have you talked to them about how do they tell, a streetcar or bus to ease up?
They're really good questions. I think I cannot speak for the PDC, so
I don't want to hijack your session, but I can answer a couple of those ones. So the data you're getting on your phone for ridership is typically an approximation done by like Google or something. So it's not necessarily accurate, but the actual numbers that I assume were provided to you by the TTC on all of their surface vehicles have I believe infrared or some type of sensor at all the doors that actually counts the number of bodies that come in and out. So they get the data not based off of people that paid because there's a lot of variation on certain routes, but actually based off the number of bodies that come on and off. So that information I'd say is 95% accurate. Yeah, the live data is not ideal. The other data is pulled later on, typically. At least that's my understanding from a couple of years ago when I was there. For the surface routes, there's usually line supervisors that manage the surface routes, usually for streetcars and buses, and they are oftentimes placed in the field managing over the radio the bunching and the frequencies between the streetcars and buses. But there's a bit of a deficiency in the way they track that information, that it's based off of the departure time and arrival time from the terminals, and what happens in between with the bunching and them going ahead or behind isn't actually tracked. And so that's more of a structural deficiency from my perspective, but I just wanted to kind of answer your questions there. Sorry for hijacking.
All actually tell them to ease up. Another example,
They
had an event in Toronto a few weeks ago.
Yeah.
The World Urban Pavilion, and people had to walk to the event. There was no streetcars on that task for 45 minutes.
This is going to be the topic of the next talk.
Yeah.
So this is really all about detecting the anomalies, not how to, encounter them and deal with them. So that's going to be
That was a great talk.
Yeah, you can talk to me during the break and I can try to help.
You have a question?
No, I just wanted to, yeah.
Yeah. You gotta go to a link.
With 15% of false predictions.
Yeah.
Are they mostly, predicting the bunching, but it doesn't occur, or are they predicting no bunching and it does occur?
Have from here, there's actually an even number of how many bunching situation that we cannot catch, like we predict at bunching, but it's actually non-bunching. And we also predict some as non-bunching bunched together. This is the number in here. We have a little bit, so we have a little bit more number of like the situation that would predict that bunching in the real situation that is non-bunched in the first place in here. So, but when we make the improvements of the algorithm, we have a like less kind of like situation that would predict the bunch as we predict it as non-bunch, but in the row where it's a bunching situation. This
More of that.
more predict that the bunching as but no bunching. Yeah. So that is kind of like a trade-off we make because sometimes we want to know bunching situation and we have to take actions for the bunching situation, but we don't have to take actions for the non-bunching. So that's the reason why we make this sacrifice kind of stuff. Yeah.
Jiha, we have one online question.
Yeah, for sure.
So somebody's asking, what were some of the data challenges that you faced?
Data challenge?
Yes.
Processing the data.
Oh yeah, processing the data. In here.
Yes, correct.
So what is the question? Like,
So the question is, what were some of the data challenges that you faced?
Okay. So for example, in the GTFS data, they update, I think every half month or like every month, but they will provide you the trip ID and also its corresponding schedule. But if you want to find those ID in the real world data, for example, the APC data and the AVO data, you cannot find those ID so that you cannot directly align the schedule with the real world collected, like how the bus is running. So, which is hard for you to figure out what the schedule offset for the bus, and also sometimes it's hard. For example, you want to strictify how the bus is running on the road because you don't want the real world collected GPS data will have a little bit shift, so it's not directly on the road defined in the shape file in the GTFS data. So you also have to find a way to align the data to the shape file so that you can see how in overall like the headway is changing or like the distance is changing between two buses. And also like to align the APC data where it's stored, like how many people is on the bus and AVL, like where the bus is still like the ID they're using to identify different buses and different, for different run is different. So that you also have to figure out the way that to matching these two data set together and then to do further data analysis. So that is kind of like the basic challenge for pre-process the data.
All right, thank you. I have another question from one of the audience. How exactly does the bunching prediction work? Are you predicting the likelihood of possible bunching on a line? How is this used to help with adjusting schedules to alleviate bunching?
So here. Yeah.
So the first portion of the question is, again, how exactly does the bunching prediction work?
So the bunching prediction is actually predicting whether it will be bunch, and non-bunching you can treat it as like a classification problem. So the input is the speed, the distance of between vehicles, and also how far and how the deviation of the current bus running from the schedule. And with those information, we are predicting actually. The prediction interval is actually I think in here is 30 seconds, and the total prediction horizon is 5 minutes, which we are making a 10 times of prediction, so that we are predicting every for 10 times all the way until like there's 5 minutes in here. So that's the reason why we have like a lot of like prediction spots in here. And with this prediction results, for example, in the 5 minutes, we predict there's a bunching, and the transit agency could, for example, take some action. For example, as you've said, maybe they can ask the following bus to slow down a little bit to like enlarge the distance between the following bus, the leading bus, and then it can somehow relieve the bunching situation in the future. That will happen in the future.
Okay. So the other part of the question is, to make it clear, do you actually just predict bunching as a yes or a no, or do you predict the likelihood of possible bunching on a line?
It predict the likelihood, but with the threshold of this likelihood, and then we like filled out to a yes or no of the bunching in the future.
Okay. And their last question is, how is this used to help with adjusting schedules to alleviate bunching?
So as I was saying, like even though it's only like a 5 minutes prediction horizon, the transit agency could take some like relief actions to the transit system. For example, they can ask the following bus to be a little bit slower, or like to stay at the station for a little bit more time, and then to enlarge the gap between this bus and this leading bus, so that it can somehow relieve the bunching situation for a little bit. But we can think of, for example, we can engage this prediction into a reinforcement learning, so that we can have a much more long, you can treat it as a long planning kind of phase, and then to improve the performance of the system.
Okay.
In some other way, yeah.
Okay,
So
thank
one
you.
last question by Eugene.
Are you planning to add external factors into the prediction, like construction, weather, accidents, when you predict bunching or delays or anything like that? External factors.
You actually account for external factors.
Construction and accident. Yeah, for sure. Like, for example, this is really interesting. So because currently we cannot like directly get those information, but for example, there's an accident really happening like in front of the bus. There have a higher probability that the bunching will build up like later upon that point on the road. So it's really needed to including those information. And for example, the weather information could also be a factor that will affect whether there will be bunching in the future. So that will be pretty helpful for us to improve the accuracy of the bunching, and also for sometimes special events. For example, there is a concert happening in the downtown area, so that could be also like increasing possibility for bunching happening in the system.
The effects of all of those really are captured in the last 10 minutes, which are the inputs into the prediction. So, the previous buses have already seen this accident that's on the road. So it's, that's kind of into the prediction.
Yeah. I think in the interest of time, thank you very much, Jia Hao. So Jia Hao will stay with us for the second presentation on another piece of his PhD work called ELSA.
Okay, so ELSA, short for Experience and Logic Integrated System for Supervisor Assistant, which is trying to answer your question is how the transit agency could control the bus running in the system. But this one is specific for incident control. So the things that motivate us is that I took a 7 days training session with TTC about like how they're training a new hired on-road supervisor, which is intended to do the control work for the transit agency. So I was thought like I will be pretty overwhelmed for the first few days if I'm really a supervisor working for the transit agency, because maybe the situation I have learned in the training session is very different from the real world situation, and in sudden there's a lot of information coming in. I have to make fast decisions, and if I try to refer to the past incident report, it's really hard for me to navigate through this kind of huge data set. And on the other side, the senior staff, like the people who give me the training, he has the wisdom, he has the experience of taking control of like making those controls. But how we can capture his wisdom, how we can capture his experience and pass that to the next generation, to the next new supervisor. So that motivates us to build up ELSA. So ELSA is trying to give both role-based and experience-based incident management suggestions using large language model. So with this application, we try to give reliable situation understanding, explainable reasoning process, and in the end, an effective decision-making process. So the methodology we are using here is the first, of course, the large language model, which is a powerful general purpose reasoner. I believe most of you maybe use this kind of like every day. But the problem for a large language model is lack of domain-specific expertise, where in this case is the detail of how specific transit agency is handling the problems in the real world. So that we are using the RAG system, which is to supply the domain knowledge within this kind of like a little bit complex, but it's basically based on the semantic similarity retrieval to inject the domain-specific knowledge into the large language model for making suggestions or making like inference or reasoning. But there's a lot of limitation for traditional RAG system. For example, a limited understanding of complex incidents, a loss of original document structure and the functional context. For example, the SOP written in the handbook is like 12 steps and in different pages. And if you treat like in chunk of the traditional RAG system, maybe the sequence is being messed up. This could be a problem for provide a reliable suggestions. And the other limitation, for example, is use the structured incident data and limited reach via rational relationship. For example, if the data set is already being constructed in a rational database, how we can like retrieve more information instead of only using the semantic similarity, but make use of the rational relationship within the data set. So that is to fix those limitations, we have proposed two advanced RAG structure. I will not go into the detail here, but for the first one is agentic-based hierarchy-aware agent RAG is basically for the SOP handbook. So instead of just searching the whole document, we actually have a large language model agents within the RAG system to summarize the section information, the subsection information, and to make a more targeted, more precise retrievement instead of like to go through the whole document instead. And the next RAG system we propose is the knowledge graph-based RAG. It's for the past experience, which in here is the incident report. So for the knowledge graph-based RAG, instead of like split the whole document into small pieces, we break the report into entities. So those entities could directly from the rational database, for example, the incident type, the event type, or we can further invert or like extract it from the neutral language that included in those reports. For example, the cause of the problem, the resources required, the action strategies, for example, the location patterns. And then we have a large language model built in this knowledge graph RAG and to connect those entities with relationship, which enable us to do a multi-hop search within this kind of like data structure. So this is example I want to give you. So this is directly from the incident report of TTC. So this problem is like a fluid leakage at the rear of the bus. And this is the knowledge graph extracted with this RAG system. So as you can see, like the red dots here labeled as mechanical, which is incident type, and the fluid leak is the event type, which is directly from the report. And the light blue dots, as you can see over there, it is the action strategy they take to relieve the problem. For example, they notify the environmental agency, they place a replacement vehicle, the operator back to the relief points, and then they have pumped the catch basin. All those stuff have been extracted and some other information is extracted as well from this nature of problem action taken parts of the report itself. And with this two advanced RAG system, we'll build up ELSA. As you can see, it's like two separate flow. On the left is we're making suggestions based on the SOP document. We call this like rule-based suggestions. And on the right is we're making suggestions based on the past experience, which is we call like experience-based suggestions. And then those two suggestions are combined together and then provide to the users. And so the data set we're using to build up this system, the first one is the TTC-SOR, which is short for TTC System Occurrence Report. It's a specific type, specific for incident report. And we have 11 types in here. In the report, there's 159 for build up the experience database, and the rest is for test. And the data, this SOR is specifically collected for Rule 29. And here is an example. As you can see, it has incident type, event type, natural problem. It has a chunk of text in here, writing in natural language, and also the action taken. And the next data set we're using here is the TTC Incident Management Handbook, which is the official training material for the new hire supervisor, including 3 parts: the guidelines which we are using to build up the external knowledge database, and the exercise question, which is come from most of the section, not all the section, but most of the section of the handbook. And we are using this to test how good ELSA could understand the SOP and answering this related questions. And the case study, you can treat it as another type of exercise question, but with more background information for help ELSA and also help the supervisor to make a more accurate decision of, like, for example, which section it should refer to answer to solve the situation in there. So let's take a look at the performance of this system. I started with the rule-based suggestions. The first element we want to evaluate is how good the system could understand which section we should refer to answering the question. Because we know like the question is directly from each section. So if we give in this question to this kind of like suggestion system, could it give us the right section in here? So as you can see on the left, on the right, the agentic RAG is representing the ELSA, which we have a 71% of the accuracy, and compared to the traditional RAG system, which only have like 55. And this 71 is not actually the limitation for ELSA. It is because for some of the section, they have really similar topics, and the questions, one question could be answered by either sections. And also, for sometimes the question itself is lack of context information. So it's not only hard for ELSA to make the decision, but it's also hard for the human to make a decision like which section it should refer to. But if we are using the case study scenarios, the ELSA could actually get a 90 out of 90, which is like 100% right to see like which section it should refer to. And talking about the accuracy of the answer. So as you can see, without any RAG system, which is the one on the very bottom here, we have a 45 or around 45 of the correct ratio. And for the system with traditional RAG, we have a slightly improvement of the accuracy, which is around like 55. And for the ELSA, as we can see there, the huge kind of lead for the ELSA, like the accuracy could improve to 90%. And not only the increasing for the accuracy, the efficiency is also improved. As you can see, without any RAG system, the reading time is a little bit long, but with traditional RAG, the information have been provided to the large language model. Some of the information is useful, but some is not. So this is increasing the reading time for large language model. But with ELSA, the more precise and the concise information is provided to the large language model so that we can see there's a huge reduce of the reading time for the large language model. So which is quite useful and quite important for us if we want to deploy this kind of system in the real world, because we treat the efficiency of this kind of decision making really important that for real-time decision making process. And move to the experience-based suggestion making. The first we want to evaluate is how good the system could identify the incident type, which could be the starting point for the search within this kind of rational database. So for traditional RAG, we can get, there's 2 scenarios we set up, but the first hit means like we only give 1 chance for the large language model to find like what kind of incident type. And the hit is that we give like 3 chances So that we can see for the traditional rack system, in the end, it is like 86% that it can get the right incident type. But for ELSA, the final hit is 97%. And come to the number, I believe there's only like 2 or 3 times that the ELSA could not get the right incident type for the whole test database. And then we want to test how similar the suggestion coming from ELSA compared to the real world action taken, so that we manually identify the action items from the action taken in the incident report. And we're using the ELSA to make action suggestions. And then we have an evaluator, which is also a large language model, to see what action item, like in the real world incident report, has been captured, has been covered by the ELSA suggestions. And to make this experiment more comprehensive, we rewrite the nature of problems on top of the original report, that we have a radio tone, which is that we try to mimic how people is talking through the radio system. And we have a different tone that it would try to express the same incident, but in a different way. So here is the results for how similar the ELSA and also compared to the traditional rack system. As we can see from the first slide, is the ELSA outperformed the traditional rack system a lot for the coverage of the action items in the real world system, in the real world reports. And even though, like for example, for the different tone, the accuracy drops a little bit, but still it is higher than 85%, which is still a quite reliable suggestions from ELSA. And then we want to perform like really interesting study, like because ELSA could provide you the SOP based on the provide you the rule-based suggestions based on the SOP documents. We want to know like how the real-world reports are following the SOP, whether it's followed or like there's some situation that is missed in the real-world reports, so that we give the nature of problem from the SOR and ask ELSA to give us the SOP. And then we use the evaluator large language model and to see what is captured, what is missed, and then we further fill those into action codes, and then we are doing some calculation for the compliance matrices, and here is the results. So as we can see, the overall compliance, like for the SOP versus the SOR, is actually 85%, which means the real world report are actually following like most of the time is following the SOP. And also on the other way, we can treat it as the ELSA SOP, it's suggested, is aligned with the real world situation. It's really practical for the real world human to follow, to build up their reports. And to the detail of the different operational categories, as we can see, the highest we get is for service operation, which is actually aligned with the purpose of SOR, which they have to have the causes, the actions they're taken to resolve the problems, and also the results it comes with, and the results are actually being take care of the second operational category, which is support and aftercare. And the one that we cannot get like a really high score for the complaints is the safety and the medical response. So what is missing? Here is the top 10 action code that has the highest missing rates in here. One thing I want to notice, I want to see the first is that only the first 6, it has the missing rate higher than 50%. The rest is actually lower than 20%, which is quite not that high. And there's 2 major reasons for why this action code is missing in the real world document. For example, the temporal stop setup, the infection control, it is being implied by some other actions in the report. For example, for the temporal stop setup, which is related to the detour situation, in the SOR, it's required the supervisor to write how, like the detour routes detail, how the bus is like going through from one road to another. So you don't have to specific we set up a temporal stop on the road. And for example, the infection control, maybe it's included in the medical related kind of actions the supervisor is doing. And some other actions, for example, PPE usage, witness contact, is actually the action the supervisor taken before it actually addressed the situation. And for the requirement of SOR is like just basically encourage the supervisor to have the action resolve the problems. So maybe those are the reasons that this kind of these two actions are missing in the real world report. But still, as we can see in here, with the SOP information provided by ELSA, we can help the supervisor to restructure their report to have maybe including more detail to perform a much more solid type of like report to avoid some other like arguments or like later if we refer those report in the future. So finally, we prepare a short demo for you, like how we can use ELSA. So here we're asking bus engine smoking, what should I do as a on-road supervisor? So ELSA, it will provide you the evidence, not only the results, but also the evidence. So it provides you the SOP, the handbook evidence, and also the past incident experience. So for the SOP, it gives you the detail which section it refers to. For example, the first one is the section E3, which is related to responding to fire, smoke, and burning oil. So which is quite related to the situation itself. And for the past incident experience, we demonstrate what entities in the dataset we refers to what relationship is related, and also, of course, the past similar incidents related to those entities and relationships. And then we gives you a easy to follow step-by-step action taken that you can maybe use to resolve the situation that you can take or reject as a human. And also you can ask follow-up questions. For example, can you give examples for a report based on the past experience? So we have complete different kind of content in here. But sometimes people just need to know some like instant answers. For example, which garage we have to pick for the operator or for the bus to report to goes back. So in here, we're asking the question, and because ELSA had a built-in memory system, so you don't have to ask the question again. And then it will give you a much more shorter answer, but precise. The garage it picked up is Mountain Dennis garage. I believe this is because like the background knowledge database is based on the report collected specific for Route 29. And if I remember correctly, like the bus ran on 29, most of those report to this garage. And that is the pickup for the real world situation and also the pickup for the for ELSA. And this is the back end of ELSA. And using this back end, you can see actually how ELSA is written for like give you the experience-based suggestions and rule-based suggestions. So after you ask the question, you can actually see how the evidence is collected, how ELSA is reasoning, and you can always going back by click any of those blocks and to see like the details of this reasoning process, make you feel more confidence or like easier for you to debug like where maybe the discussion is not aligned with your expectations, so you can see like what is wrong with this reasoning process. So still a lot of limitation in the future work, but given the time limits, I will not go into the detail of this. And if you're interested, we can talk about this more later. And that's it for ELSA. Thank you.
Thank you, Jiahao. So floor is open for questions to Jiahao on ELSA. Also online, those with us online.
No, any questions so far? Waiting for questions.
One quick clarification and repetition. What is SOR again?
Oh, SOR is this is an occurrence report. Is the another phase like
That's not
documentation.
Okay.
Yeah, it's in the report.
As opposed to SOPs sort of scenarios and then response to those scenarios.
One's reality of what happened, and other is a framework for answering.
Yeah, it's from the training manual.
Yes.
And operating.
Yes,
Okay.
Yes, sir.
So the examples, the case studies you looked at were sort of static one-offs, like, broken bus or the fuel and so forth. But this also applies to the previous presentation that for dealing with bunching and gapping and so forth. And I was just wondering whether, a digital twin would be useful for training purposes, for answering, for training supervisors for dealing with more complex issues of gapping and bunching, as opposed to the ones you've got are pretty, straightforward in terms of the steps that have to be followed, while the other, operational control decisions are require knowledge about a wider range of things in terms of previous buses and weather and whatever. So
Yeah. So that actually is our like future research interesting. Like we are trying to embed the reinforcement learning, where we using the reinforcement learning to give control to the bunching and overcrowding, like how the operator should, the controller should do to the system. And we're using ELSA to give you the reason why we're taking these actions. So for example, we asked bus to hold for 5 minutes based on the results coming from the reinforcement learning model, but why we're taking these actions. So we are trying to using ELSA based on the overall understanding of the system and also the performance and also the real-time running situation. And then we give you the reason why we're taking these actions. So it's another kind of like perspective of ELSA in the future. Yeah. Thank you.
On sort of the future work, they're talking about Grok 5 being able to take real-time video in and understand what's going on.
Yeah.
That would be amazing, because you could actually be taking real-time feed and providing real-time, suggestions.
Yes.
I hope you will have time to work on that.
Yeah, for sure.
I think it's March or something when that becomes available. I don't know.
So actually, we're trying to engage a multimodal large language model that we can actually taking pictures and videos and video calls, like voice informations, and convert that into text, and then we are using those information as the input to ELSA and to make further decisions and further suggestions. So that could be like in the near future what we could do for ELSA and to make it more powerful. Yeah.
Thank you. That was really great, really impressive. I have a couple of questions. I think I just answered one of them. So you actually ran this many operators in real life sort of scenarios, or not really? It looks like the answer is no, but still kind of curious.
Sorry,
If you can repeat the question.
yeah.
Have you shared this or no?
Sure.
Actually, we printed this work to TTC before, but actually this is not going to be like applied project already, but maybe in the future, like for example, in the transit town, in AI transit town, or like if TTC interested, we can, for sure, we can talk about like in the future collaboration for this project.
Very cool. And then all. But remember the role in the for that or hold for that, or what that like give you?
Asking like if
there's a rolling it out to the street.
Yeah.
Oh, yeah.
What's the long-term goal for this for you? Do you plan on making it available? Are you going to sell it? You're not sure yet? Because I see a lot of utility here.
Well, again, this really is related to what I was talking about before, that we have a lot of solutions, but unfortunately, there hasn't really been a mechanism by which we can transfer this to the industry and roll it out to the industry. That's why, this whole idea of AI transit town, and this is in collaboration with the TTC and Opta. But we're inviting everyone who's interested in this to really help us set it up, because this will really be the vehicle to transfer those solutions to the industry as first prototypes and then full commercial products. But unfortunately, at this point, we presented this work to the TTC. There's a great deal of interest. We'll be happy to talk to Metrolinx if there is also interest in something like this. Customize a tool for your own purposes.
Thank you. I'll come talk to you.
Thank you, Jiahao.
Do you think there customer satisfaction field? So customer satisfaction is, the inputs is not as structured as like incident management. There's no like incident code. So what's your perspective on that? And if so, if you think it's useful, what kind of data prerequisite would you require for this RAG-based system?
This is really interesting question. And actually, we have a previous project called Transit Pass. And we have a paper already actually published online. So you can search for Transit Pass and U of T. You may find those papers. So that paper is about like using the social media posts as the source for understanding the customer satisfaction. So we also bring to another level, like traditional like satisfaction for overall performance of the system, right? But for the social media post, sometimes people is mentioning where they're encountering those problems, where they feel unsatisfied. So we further extracting information, not only whether it's positive or negative, or like neutral, or like whether it's sarcasm or not, but we're also extracting what is the problem they're facing and also where they're facing those problems. And from a non-structured information, we're using large language model to extract the information and to put those into a JSON file, which is a structured kind of database. And then we can perform the data analysis based upon the JSON file instead of like based on the unstructured text. And then we can understand, for example, which station is the most problematic stations has like, and also like when this situation happening, like the people feel most unsatisfied and things like that. We have like much more detailed like explanation of those technologies and terms we're using like in the paper we published. And thank you.
Okay, and any questions online? No? Okay.
Nope.
Okay. Well, okay, thank you very much, Jiahao. Okay, the next presenter is next presenter is Diego Da Silva, who's a postdoctoral fellow at the Transit Analytics Lab. And he holds a PhD in computer science, and his research leverages scientific computing, data-driven analytics, and AI to advance public transportation planning, management, and operations. So Diego also brings extensive private sector experience in data architecture, systems design, digital transformation, and IT project management across finance, insurance, telecommunications, and a number of other sectors. So Diego is going to talk to us today about a very interesting study in which he's really envisioning the data architecture that will enable and support AI-powered and AI-driven solutions at the organizational level. So thank you, Melissa. Welcome.
Hello, everyone. Good morning. Yeah, I see some faces here that we met in August. So the presentation today is data architecture for AI-ready. I want to click a little bit this title because I think it's very informative. Well, so data architecture, why this is important? Right now you see like how many tools. Yeah, yesterday we saw like so many different tools and machine learning models, deep learning. And we feel that we are in this moment that we need to work more in orchestration than on the solutions per se. So that's why data architecture is fundamental for this transition. I'm not only saying this for public transportation, but the whole industry is changing as well. So it's really important to consider how to organize the components and the logical organization of the company. Yeah, so that's why I want to focus. The second part of this title here is the AI ready. And why AI-ready transit agency now is extremely important, this scenario that we are living right now. Because AI will not change only the solutions. AI will change the architecture as well. So the way that the components that we will interact, this will change as well. Yeah, today we know how we build. Like people that work on the information technology, they know how things work, what are the techniques and methods that we need to implement your system. But recently, with the AI engineering pipelines, this will change because now we have MCP or agent-to-agent communication. This will change. And why this will change? Because this brings like some benefit. You need to code less and you make your system more intelligent to interact with the other subsystems or solutions within your data architecture. And the third part is the ecosystem. Yeah. Public transportation, it doesn't exist. It's not self-contained. Actually needs to interact. This interaction is really important. It's not only among transit agencies, but also university, transit agency, or partners or third parties and agencies. So we need to build this relationship. And this relationship will be sustainable if you have a common language, if you have specifications. And then I'll talk about a little bit of the role of specifications, mostly the GTFS, which is one of the main standards that we have. Not kind of standard, but it's a specification for a common language in transportation, and how in the AI environment, the GTFS is really important to establish some standardization of how to communicate system to system, okay? Let's start from the motivation. So the first thing, as I explained, we are living this digital revolution. So this is crucial for public transportation. As I said, this is not unique in the industry. Everyone is feeling this transformation coming, but the problem is how to prepare for this transformation. The second thing is data. Yeah, everyone talks about data, but data, although is the field of those algorithms, the systems and the solutions that we want to build, it also brings like some problems, yeah? And then you'll talk about the paradox of the big data, the volume. We need to understand that transportation agencies and many of the public services, they are producers of, they produce data, yeah? So that's why this role is extremely important, and the interaction with other parties is important in this ecosystem that we'll talk later. Third challenge here, the third motivation is how to orchestrate this data-intensive ecosystem. As I said, data architecture is about orchestration, yeah? And because of this orchestration demands some technical knowledge, I think right now what we are seeing with AI tools is how we can make those tools available, not only in terms of solution, as I said, but also how can we connect this in a larger picture. We talk, for example, the AI transit TAO, and I will explain a little bit more at the end of this presentation, how can we build, and as a good example, how to interact with different entities. It's also, this is an opportunity for public transportation, yeah? And every time, and this is my experience working in the industry as well, every time when you need to upgrade some system, let's say, for example, in transportation fare system, this is a huge opportunity, mostly because these new technologies that now are available, they integrate multiple solutions. Sometimes they have AI embedded in those systems. So this means that if you are not ready to accommodate these new solutions, and I mean ready means the orchestration, the data organization, how can you process this data, how can you split this data or compute those solutions? So you will be locked in a design that will not scale. And even if you are aiming, for example, for mobility as a service, which is a terminology that everyone really wants to connect and wants to implement, but then mobility as a service has two components. We have the operation, like the transit side, but it has a huge part in technology as well. So we need to integrate those two in order to achieve this goal as a whole, okay? And that's why we are here to advocate for a domain-specific data architecture that takes into account the public transportation goals, but also the transit data challenge. And I know that sometimes it's easy for us to look to other industries and try to incorporate some solutions for other industries, but we need to understand that public transportation is unique in many aspects. And when it comes to data, this is really important to understand because, for example, let's take fare systems. Fare system, we have in a very short time, millions of transactions happening in 2 hours. This is massive. And if you are trying to build, for example, predictions or estimation, we need a system that needs to work in a very fast way. So this is not trivial. So there are some architectural problems that we need to account. And that's why I think this forum here, this symposium is important because when you show and highlight the problems that we are facing, we can come up with some ideas and maybe we can trying to integrate this or maybe create a forum specific for data architecture. So this is one of the things that we are trying to advocate here. And what are the challenges that we are facing right now? So we have two new paradigms. The first one is how to model. The way that we model changed and changed dramatically. So first one here, we have the first workflow, which is the machine learning workflow. This is the traditional. When you are talking about AI, we have two main workflows. We have the traditional one, where we start from the data, and then you build the model and then the solution. And the second one, which is the foundational models. So for example, Jihao mentioned the large language models can be a time series foundational model. So we start from the prototype, then you collect the data. So you test first, and then you collect the data, and then you build the solution. The second part is that data is just a layer in the enterprise architecture. That's why we are focused on this layer right now, because we need to understand how to ingest, how to integrate, how to store the data, how to consume. And of course, it depends on the design. But then you have the data governance. I will mention, this is extremely important, the data governance, security, and metadata. And this can be a roadblock, for example, for most of the solutions that we are talking, like this morning, like when Jihao present, for example, his work, or even like the works that were presented yesterday. How can we integrate those solutions in enterprise architecture? This is not easy. Yes, when you see like those results and then we try to implement, and I did this multiple times as a consultant as well, the reality is different. When you see the business constraints is not take the solution the way it is and implement in your architecture. This is not, will not work. Then we have the big data paradox, yeah? We always talk about the volume. Volume is important. We have lots of data, we don't know what to do. But what is the quality of this data? Yeah, we already know garbage in, garbage out. But also this terminology of big data paradox, coined by Meng, says that if the probability of finding a statistically significant but meaningless relationship also grows with big data. So you can find, of course, you reduce one type of error, but then you increase another one, like those that were not detectable when you were in the small data world. Yeah. And how transit data is organized? Well, I think some of you work with data. We have some data scientists, we have data analysts. It's not easy. I'm citing here one of our gurus in data, Brandon. So the first part in his report in 2015, he highlighted this limited fee.
Sorry, guys, I think we were just having some connection problems. We'll be back in a couple of minutes.
Okay, so I take this example here because ARKit is one of the ITS architecture that usually is one of the examples used in US. And as you can see, we have different like subsystems, but when it comes to data, you have this huge block here, sending data to this monolithic, I would say, because it is not clear when you read the documentation, the ARKit, but it implies that you need to design your architecture as a whole block. And this is actually the reality. When you go to transit agencies, they try to understand the data architecture. This is usually the reality. You have this big block, and this big block, of course, creates like some rigid structure, which is really a drawback for innovation as well. So that's why we need to break those blocks. So we have here two approaches. One is the data architecture, and the second one is the topology. So the data architecture is concerned with service autonomy and also decouple the subsystems. Okay. The second part is the data distribution and computation. Okay. So this part is more the infrastructure. So how we compute, how you distribute your data. So we have these two decisions when it comes to data architecture. And then we come up with this chart here. How to connect data topology and data architecture to transit goals. In data architecture, we always have this, there's a terminology that we use, which is ilities. Ilities is the goals, because our data architecture is also is always a trade-off. We need to decide. You don't get the optimized data architecture or software architecture. You have an architecture that will attend some criteria that you define. Okay, so how can you connect these to transit goals? I think, and this was my choice here, I'm connecting to transit interoperability. And why this is important? Because then there are some goals connected to interoperability. If you are in this low here, like, for example, monolithic decentralized topology and architecture, and then no interoperability, this means that you're basically working within your own system. So you're not interacting with anyone. Yeah. And we see this even like in region, like metropolitan areas, some kind of isolation. Yeah. So basically the transit agencies, they work, and this is not in terms of the policies, yeah, because they are integrated in terms of policies. But when it comes to data architecture, they are not integrated. Each one has their own IT services. They have their own servers. They have everything separated. So what we are trying to advocate here is that there is a huge opportunity to build just one system, just one IT service, because we don't need to couple this to the policy. Yeah, we can't decouple this. It's an opportunity as well to reduce cost. And then we have this transitions here. We have the first, the y-axis, the flexibility, and the x-axis, the interoperability. So when you grows here, when you go to this y-axis,
you are decoupling the system. What this means? This means that I'm going from a monolithic more to a decentralized or per service or domain architecture. And also the way that you can process your data is decentralized, distributed, or federated. It depends on the goal. Okay, that's why we need to connect this to interoperability.
but also we have the cost, yeah? And this is one of the main drawbacks when we talk to data architecture architects. They say, no, it's too expensive to maintain, for example, a per service or microservice. It's impossible. We understand that implementation cost is really high, yeah? But maintenance will go down. And when you have a more distributed. Why? Because, for example, every time when you need to deploy a new solution, you don't need to down your whole service. Like probably people that work in a monolithic, centralized company or where the logical architecture is designed this way, we know that when IT needs to implement a new solution, it can be like a new component, they say, okay, the services are not available for, I don't know how many hours. So this will impact, of course, operation. But when you have a decentralized, actually you just down the service that you are working. So you don't need to impact the whole company, only the ones that will be updated, okay? So this is the rationale here for this chart. And then we connect this to AI solutions. So how this monolithic centralized will enable in terms of AI. So if you are here, in the monolithic centralized, you are
in the book of the descriptive analysis. So this is the maximum that you can do, yeah?
If you go here, so this is what we call the transitional. The transitional is when you have like some, the organization understood that we need to change the architecture, but also the way that you compute. So we have some for example, domain-based and distributed or monolithic federated or per service and distributed. So these are kind of options that we have in the 2D that I mentioned, the topology versus architecture and the interoperability axis here. And what this is enabling for us, medium integration for the interoperability, but also in terms of AI, mobility as a service, digital twins, integrated AI pipelines. And this is like a cross-domain, across transit agencies. We can now work in integrated as a one system, okay? And then we have what we call the, let me go here, to the integrator. The integrator is the ultimate and more evolutionary architecture that we call, because this will be more flexible. Flexible in terms of computation and flexible in terms of how you can modify and adapt to new solutions. And that's why this is perfect for AI, because then now I can run my models without being locked in some solutions. Yeah, so this is, I think, and of course, this is not for every single transit agency in the region, probably for the leaders. For example, let's say Metrolinx here is one integrator, can be the leader of this process to how can we work and share data across multiple transit agencies. Of course, as I said, this is not a technical computational discussion. We need to connect this to transportation. And we know how transportation works. Transportation the goals of the region, because in a short term here, we are building architecture design, which means like the components to get here, the architecture style. So if you plan, for example, a more flexible architecture to integrate AI solutions in the future, so you need to work and connect the architecture goals to the transportation, the public transportation goals. So this is an example. Of course, we need to talk more. I don't have time to cover everything, but just to give an example, as I mentioned, we want to bridge the research and the industry. How can we do this? Yeah, we saw this morning like ELSA, then Corinne will talk about Tolybus, IROM, T-Spark. So these are solutions that we design here at U of T. And then, of course, our eyes are shining and say, oh, I want to implement this. I want to incorporate this in my architecture. So we have the inputs here, because these tools, they need data. And then you have the outputs here, the solutions. And of course, one option is to build like this on the cloud. Yeah.
And then build the external data governance. How can we do this effectively, thinking in terms of the chart that I shared with you?
We have the first one, which is one-to-one communication. Can be, for example, transit agency to university, one example. So we have the architecture style here, monolithic. Then we have a centralized database that can be on the cloud. And then we have the AI models here that the transit agencies will consume. This is one option, one-to-one. So for example, U of T, DTC. Now we have the second option here.
We have multiple transit agencies in their monolithic transit architectures. Then we need a layer of data transformation. This is really important because
working with different transit agencies, we know that the data is different and they have different names, different fields for the same thing. So you need to integrate this. Then this layer here is really important because this is, I think, is the new role of specifications, GTFS, TIDES. They will work here, trying to standardize the names and standardize the data, and then this will be consumed here in the federated, it can be federated or can be centralized. And then the AI models connecting here. Then we have the third option here. Let's say that one of the transit agencies, they want to install this in their system. So this will be part of a component of their data architecture. In this case,
instead of all the solution, we need to send a package. So we'll
package this for the transit agencies to install this. And why this is important to change and think in terms of architecture here? Because every time when you are adding more components and solutions in your architecture, you need to orchestrate. And this means that you can work as a monolithic and you have this ad hoc solutions running in multiple machines that are not scalable, and this will be a problem in the future. Or we can start thinking how to change the domain here. Like, for example, can be domain or per service. Then you modify the architecture to accommodate these solutions in the future. Okay?
The last slide. We are experiencing this transformation right now, and we need to be prepared for an AI architecture. Yeah. And this is really important, as I said. It's not the same way that we are dealing with systems today. It's completely different. AI technology is constantly evolving, and we need to accommodate this evolution. And that's why we need flexible architecture that can be evolutionary, that can be adaptable for any solution that will happen in the future. Their architecture decisions, they need to be aligned to some goals, to other goals. They will not exist in isolation. So if you don't have your AI in your public transportation goals,
I think we need to review this part. And the path to a flexible AI-ready architecture is not made in a single leap. We need to go slowly. So go from your block to a transitional architecture, and then you see if the next step is for you. Okay? Thank you very much.
Floor is open for questions as usual, from online or here.
I know Brendan's itching to ask.
Yeah, go ahead.
Okay, I guess I have two questions. It's fascinating. The first one, as you move into your diagram, centralized monolithic to the federated, or I'm not sure what the top right-hand corner was. Is there not a challenge with cybersecurity? Isn't the centralized monolithic easier to protect data and access to that data than if you have an open system with multiple agents? So that's one question, because cybersecurity is preeminent concern of everybody. The second one is, I mean, you've illustrated very well how additional complexities with mobility as a service, because you're right, it would take this, and there have been baby steps. I mean, it was much hype and not, and you know, it's not achieved what people were anticipating, and I think it's because they underestimated how complicated it was from an organizational point of view and technical point of view. Some places have done the baby steps using the fare collection system and account-based ticketing to basically add on, but that's just for fares. It is not your vision of an AI-based system that would have all the data available to everybody so that you could use new AI tools. The big problem is there's no institution that does this. You suggested, you know, the largest agency in a region, and that's sort of the way we're sort of ending up going. But that's only, you know, most agencies do not want to share data. And so without a regional institution that has that responsibility, sort of like, you know, in the European model, the authority is a basis, but in North America, that's very hard to conceive how you could get to that situation. So,
Brendan, the two topics that you brought is really important. The first one, cybersecurity, and I totally agree. When it comes to data, and this is part of the data governance, we need to understand like the whole pipeline. Yeah, it's not only the data ingestion, collection, processing, but also security, governance, metadata. There are many multiple steps. And the problem is, and this is comparing the industry, yeah, and the public transportation. This is kind of sometimes when I work in the industry, when I compare to public transportation, I don't see the reflection sometimes. Like some of the good things that I see in the industry, they are not in the public transportation. And one of the things is data governance. And this is something that not all, and when you understand what is the data governance role, this changes from industry to industry as well. And sometimes the data governance is more like how to control the data, but not like an active participation on the goals of the company. And this is fundamental that any company, and I'm saying that banks, insurance companies, can be tech companies, they don't give any step forward if they don't talk to data architects or data governance. They don't implement things just because they want or just because of the solution. Data architecture, data governance, they are part of the solution and they need to be so I don't see the same maturity in public transportation. I think, of course, we are getting there. And in terms of solution, when you mention cybersecurity is in the layer of technology. So we are in the first layer that enable the whole enterprise architecture. Cybersecurity is more components, it's more physical and more logic, how we deal with the data. So if you were, like, for example, public transportation or prioritize policies or the rules inside of the solution, then you have the conflict sometimes. Yeah, so this is common most of the companies when you have IT entity that says, no, we don't do this because this is not permitted here because
security issues. But also how you include the security team to understand the goals of the company, because sometimes they are just in their own space, their own boxes. They don't see what their role is connected to the whole picture. So we need to bring people in like the table and discuss this together. And that's why I think cybersecurity can be a problem if you don't connect them to the goals. Yeah. So if you connect, they know the role and how to enable those solutions to get the goals that the company with that. So the second thing that you mentioned is related to
the lack of an institutional, regional, where multiple
Yeah.
operators, multiple modes,
Yeah, understand. Yeah.
data. I mean, here we have the data management group, but they actually are the source of data.
Yeah.
Transit, there's all sorts of sources of data.
Yeah, and you gave an example for that in Europe. And this is true like any country. So anywhere you go, public transportation, and this depends even like, for example, how you define the public transportation in the law and the constitution, or like how you define this service in the country, in the city. So there are many things that and it brings also the question that you always pose when you are presenting in public transportation, a private company, streaming, or as a public service, what kind of service? It's hybrid, yeah, it's both. So we need to understand that we need to keep the service, because the public part of the service is that we are serving people. Yeah, so this is the main part. So we need to serve people. And the second part is we need to manage also. We need to manage the operations, we need to pay people, so this whole thing. But how this connects to the design, like the whole design, how this can operate here. Of course,